Okay, so a device for impact testing consists of a 34 kilogram pendulum with a mass center G at G, with radius of gyration about O is given. So the radius of gyration is just related to the moment of inertia, IOZZ, as such. The distance B for the pendulum is selected so that the force on the bearing at O has the least possible value during impact, with the specimen at the bottom of the swing. Determine B and calculate the magnitude of the total force R on the bearing at O at the instant after it's released from rest at theta is equal to 60 degrees. Okay. So first they're telling us that the distance B for the pendulum is selected so that the force on the bearing at O has the least possible value during impact, with the specimen at the bottom of the swing, the specimen here. What does this mean? Well, this has to do with the concept of the center of percussion. The idea is we're gonna take a simplified system that if I have a pendulum and I'm impacting the pendulum at this point, the pendulum without the pin is gonna move like that. If the pin was not there, the pendulum would tend to deform like that, meaning that the reaction force at O would look like this. But if I take the same pendulum and if I impact it here low enough, at a location low enough, then the pendulum is gonna tend, if the pin is not there, the pendulum is gonna tend to move like this, rotate this way, meaning that the reaction force at O, its horizontal component points rightwards. So of course the reaction force at O also has a vertical component to counteract the weight. This does not have anything to do with the horizontal impact force. However, the location of the impact force changes, flips even the horizontal component of the reaction force at O. This means that there is an optimal location on the pendulum where the impact force, so that when the pendulum is impacted at this location, the reaction force at O is 0. Okay, this point is called the center of percussion, and this concept is applicable using machines like this, but also in everyday kind of usage. If, for example, you're playing tennis, then somehow you want the ball to hit the racket somewhere where so that the reaction force at your hand is minimum, so that the racket does not fall. Same thing for like a baseball bat. There's a location on the bat where if the ball hits the bat at this location, the force at your hand, the force that you need to grab the bat with, is gonna be minimum. So this is what's happening here. This distance B is chosen so that when this hammer impacts the specimen, the reaction force at O, the horizontal component of it, is 0, so that the reaction force at O is minimized. During impact, if I want to draw the free body diagram during impact, okay, this is how my system looks like. And the point G is here. So if I want to draw the forces now, I have a reaction force at O. We said the horizontal component of that is 0 because we're selecting B that way, so that the reaction force at O now is vertical. And I should have drawn it kind of nicely, but this lies at the same kind of vertical level as G. The weight is like this, and we have an impact force, a horizontal impact force. Okay, that's awesome. So this says if I name this point, so this point is O, this point is G, this point is P. If I name this point P, the sum of moments about P is always equal to 0 during impact. Impact. So from the angular momentum equation about any point, we have that MP is H dot P plus VP minus VC crossed with G is equal to H dot C plus RC minus RP crossed with MAC. Okay, so if I use this form of this equation here, and I have MP is equal to 0, then I have 0 is equal to H dot C plus RC minus RP cross MAC. H dot C is equal to ICZZ alpha E Z, and RC minus RP is so at the vertical position during impact, RC minus RP is this vector, which is equal to BEY. So this is EX and this is EY. Okay, the acceleration of the center of mass C, I can write it as AC minus AO is equal to alpha cross RC minus RO plus omega cross RC minus RO. O is a fixed point, so AC is alpha EZ crossed RC minus RO is this vector in the vertical. So during impact, RC minus RO is minus 0.6 EY plus omega EZ cross omega EZ cross minus 0.6 EY. So that, calculating the cross products, we get minus alpha 0.6 EX EZ plus. And then plus 0.6 EY omega squared, because EZ cross EY is minus EX and EZ cross EX is EY. Very good. So this is equal to BEY crossed with 0.6 alpha EX plus 0.6 omega squared EY. Just calculating the cross product, that's along EZ is equal to ICZZ alpha plus, actually minus 0.6 B. I can take alpha as a common factor here. So that's actually equal to 0. Okay, which means that ICZZ minus 0.6b is equal to 0, because we know that alpha is not 0. So then this will enable us to calculate b. B is ICZZ over 0.6. The only issue left here is that we are not given ICZZ, we're given IOZZ. We're going to have to use the parallel axis theorem to relate the two. IOZZ is equal to ICZZ plus the mass of the device times the distance between C and O squared, which is 0.6 squared. Okay, so now we have everything we need. We can calculate B. That's the first part of the problem. Again, we are calculating B based on the fact that B is located at the center of percussion, meaning that during impact with the specimen, the reaction force at O is purely vertical. Because of this information, during impact, the sum of moments about P is 0, and we can use this information to calculate B. The second part of the problem is to determine the total reaction force R on the bearing O at the instant after release from rest. I will pause this video and I will solve the second part in another video.